Welcome.
Thank
First
you.
of all, thanks for your beautiful talk.
Thank you.
So we'll first go a bit more about the history about how you came into the field, because you published the first or one of the biggest organ chip papers in 2010, but when it was still a very young field. So what actually motivated you to start in this field of organ chip?
Yeah, so there's a little bit of history to how I started, working on organ-on-chip technology. So during my doctoral research, I worked with Professor Shu Takayama, who was at the time at the University of Michigan. And in his lab, I was introduced to the field of microfluidics as a nascent field at the time. But I also had an opportunity to kind of explore this idea of using microfabricated devices for cell culture. So that led to an interesting paper and interesting project. But through that paper, I actually got connected with Professor Donninger at Harvard at the time. So I was recruited to his lab to start a new kind of initiative, actually focused on developing human lung models for environmental screening. So that's how we came up with this idea of creating breathing lung on a chip that we describe in the paper.
Right, cool. And so it's been a while since that. I mean, it's almost 15 years now since
Right.
that has been published. What were some of the major hurdles that you had to overcome, and how are they now overcome within the field?
Right. So if I try to recall what it was like to work in the field 5 years ago or 7 years ago, a lot of focus was on still demonstrating the proof of concept of this technology, and a lot of emphasis was on validating the relevance of these model systems. So one could always get the cells and put them in microfluidic devices, grow them to engineer tissues, but at the end of the day, the question is, you know how close are they to the real things? So we used to spend a lot of time not only creating these model systems, but also analyzing, measuring responses for validation purposes. So I would say that was one of the major challenges we as a field, have confronted and we had to overcome.
So then also on a bit of a different aspect. So you've also shown in your presentation that you are now working a lot with organoids. So where do you see the major advantages of these organoids within, well, the technology of organal chip?
Many people know organoids, by definition, they're derived from stem cell. They have the ability to self-organize into very mature tissues. So trying to do these kinds of things in conventional in vitro flask culture, dish culture models is nearly impossible. So being able to recapitulate that native complexity, still, using very simple techniques, I think it's really the greatest advantage of organoid technology. So now, how actually does it fit into the field of organs on chips? So organ on a chip, as everyone knows, kind of based on this idea of using microengineered, microfabricated devices to really precisely control the microenvironment of cells that we culture. So imagine you culture these stem cells in 3D environment, created in a microfabricated, microengineered device. So by doing this, you basically take the best of both worlds. So you get actually the inherent ability of stem cells, to form very complex physiological tissues. But at the same time, by using these microfabricated devices, you are now able to tightly control the local environment of these developing stem cells. And as a result, chances are we will be able to produce more realistic and more controllable engineered tissues that can be used for a variety of applications.
What do you think will be like first of all, do you think that there is an application of artificial intelligence or AI within organ chips? And if so, how do you think that this will further drive the field?
So I believe it's not, immediately easy to answer that question, but I'd like to point out the fact that there are a couple of hurdles to overcome before we get to that stage. Many of these organ chip models, in their current forms, suffer from limited throughput and also limited reproducibility. So I think it's critical actually to be able to produce these devices in a highly reproducible manner and also conduct experiments to get reproducible data. And also scalability is another major issue. Right now, so there's an irony in this field where it's really the complexity that people are very excited about. This technology being able to mimic complex things happening in the body in these man-made systems is very exciting. But if you think about it, it's also the complexity that makes it really difficult to translate this technology into industry practice. So one of the major issues is like the scalability. It's not very easy to scale up, scale these very complex tissue culture devices and experiments. So I think we would have to come up with ways to scale up the production of these chips and also experimentation using these devices. So if we could solve these two problems, reproducibility and scalability, then what's really exciting there is we will be able to start generating a large amounts of data, sufficiently large amounts of data that we would need to make accurate preclinical predictions or to understand complex biological processes happening in the body. So with those actually issues resolved, then I personally think the possibilities are limitless. So I always use the Tesla analogy. So one of the reasons why Tesla has been able to lead the field of autonomous driving is because these Tesla vehicles around the world, they actually capture data from a daily driving. They send those pictures and data back to the headquarters, where they actually use those high quality realistic data to train their autonomous self-driving algorithms and so on. So in biology and medicine, we have not been able to do that because we get data from animal models or very limited, oversimplified cell culture models. With scalable and reproducible organ chip model systems, up and running, I'm very excited with the possibility that we will be able to get very high quality, human relevant data at scale, and using those actually high quality, human scale data or AI scale data, we will be able to train AI, algorithms to make, predictions or to further understand the complexity of the human body in health and disease. Yeah.
Okay, cool. Well, I think this was it. And well, once again, thank you.
Yeah, thank
and
you.
I hope you enjoyed the conference.
All right, thank you.